The universe is a vast and complex thing that many consider a miracle that gave us life. But as fate has it, it will not last forever. Our galaxy will end eventually. It's just a matter of how. There are multiple theories ranging from religious ends to scientific ones such as the Big Crunch or Big Freeze of the universe. But today, I want to talk about a theory I have not heard before. The Big Rip. Before we dive into our universe's end, we must first explore how we began. I'm going to go with the theory of the Big Bang to explain our universe's origin, as it is one of the most credible theories of how we came to be. As I stated, the universe is vast and complex. It began in a state that defies imagination, an infinitely hot, dense point often referred to as a singularity. The theory that describes this incredible transformation from nothing into everything is known as the Big Bang Theory. Far from just being an explosion of matter into empty space, the Big Bang marks the rapid expansion of space itself, giving birth to time, matter, energy, and all the laws of physics as we know them. Now we will go over essentially a timeline of time. At time 0, the universe didn't exist in any familiar sense. There was no space, no time, no atoms, no light. Everything was compressed into a singularity, where the laws of physics as we currently understand them break down. Then, for reasons at the time unknown, the singularity began to expand. This wasn't an explosion in space, but rather an expansion of space itself. The moment this expansion began is what we call the Big Bang. From this first instant, the universe started growing rapidly in a process called cosmic inflation, which is an ultra-fast exponential expansion of space that occurred within the first fraction of a second. During inflation, the universe expanded faster than the speed of light, not violating any laws since it was space itself stretching, not objects moving through space. As the universe expanded, it cooled just enough for energy to start transforming into subatomic particles. During the first second, the universe was a chaotic soup of fundamental particles, such as quarks and leptons, which were like electrons, photons, and force-carrying particles. By around 1 second, quarks began to combine into protons and neutrons, which are the building blocks of the atomic nuclei. The balance between matter and antimatter tipped slightly in favor of matter, for reasons still being explored, and this asymmetry is why we even exist. Over approximately the next 20 minutes after the initial Big Bang, the universe has cooled enough for nuclear fusion to occur. Protons and neutrons fuse into the first atomic nuclei, mostly hydrogen and some helium and trace amounts of lithium. This process is called the Big Bang nucleosynthesis, and the proportions of these elements are still measurable today, matching predictions with incredible accuracy. For hundreds of thousands of years, the universe was still too hot for atoms to form. Instead, electrons floated freely, constantly scattering light, photons, making the universe essentially opaque, like a glowing fog. But at around 380,000 years later after the initial Big Bang, the temperature dropped enough, roughly around 3000 Kelvin, for electrons to bind with nuclei, forming the first neutral atoms. This event became known as the recombination, allowing light to travel freely through space for the first time, and the universe became transparent. The light from this moment is still traveling through the cosmos today, stretched into microwaves by the ongoing expansion of space. We detect it as cosmic microwave background, or CMB, radiation. A faint glow in every direction and one of the strongest pieces of evidence supporting the Big Bang Theory. Once the neutral atoms formed, the universe entered what's called the Cosmic Dark Ages, which is a period before the first stars were ignited. Slowly, gravity began pulling matter into clumps. These clumps grew denser over millions of years, eventually becoming the first stars around 100 to 200 million years after the Big Bang. Stars grouped into galaxies, and galaxies formed into clusters and filaments, building the large-scale structure of the universe. Inside stars, heavier elements like carbon, oxygen, and iron were created through nuclear fusion. These elements would eventually form planets, moons, and even the atoms in our own bodies. Then about 9 billion years after the Big Bang, one of the newer stars formed with a surrounding disk of gas and dust, our Sun. From the leftover material in that disk, the Earth and the rest of the solar system came together about 4.6 billion years ago, and life on Earth appeared within the next billion years. Over eons, that life evolved into sentient beings capable of asking big questions about the cosmos. Humans, wondering where it all began. Now, this video isn't about why the Big Bang Theory is a good theory and a valid option for how the universe began, but here is some proof, supported by strong scientific evidence, of why the Big Bang Theory could be correct for how our universe originated. The expansion of the universe and the galaxies moving farther away from us, and the farther they are, the faster they move. That was first observed by Edwin Hubble in the 1920s, prompting us to believe that space is expanding. Furthermore, the amounts of hydrogen, helium, and lithium in the universe align with calculations from the Big Bang nucleosynthesis, and the distribution of galaxies and cosmic voids is consistent with early fluctuations in the CMB. Speaking of CMB, that was first detected in 1965 by Arnold Penzias and Robert Wilson, which the CMB is a literal snapshot of the early universe and proves when it was first discovered, and helps us understand the distribution of galaxies and cosmic voids, like I said earlier. Let's also look at an influential astrophysicist's perspective on this, Neil deGrasse Tyson. He often says the Big Bang didn't just give rise to matter, it gave rise to us. The atoms in your body, carbon, nitrogen, oxygen, and more, were forged in the stars that formed from the material created in the Big Bang. You are, in the most literal sense, made of stardust. However, with the origin of the universe explained, let's dive into the whole purpose of this video. One of the ways the universe may end. In a big rip. Do you remember earlier in this video when I stated that everything started when the singularity started expanding for a, at the time, unknown reason? The universe's expansion could have been the result of something called dark energy. In the vast, ever-growing cosmos, there exists a phenomenon so powerful, so mysterious, that it challenges our understanding of the very fabric of reality, known simply as dark energy. This invisible force is believed to make up nearly 68% of the entire universe, yet its true nature remains one of the greatest unsolved puzzles in modern astrophysics. The concept of dark energy emerged in the late 1990s when two independent teams of astronomers made a groundbreaking discovery. By observing a distant type Ia supernovae, which serve as cosmic standard candles for measuring distances, scientists expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite. The universe's expansion was not just continuing, it was accelerating. This unexpected finding shook the scientific community. Something unseen was working against gravity, pushing galaxies away from one another at an ever-increasing speed. That unknown force was given a name: dark energy. Despite its name, dark energy is not simply dark. It is not visible, nor does it interact with matter or light in any conventional way. It does not clump like matter or have a detectable mass. In fact, scientists do not yet know what dark energy actually is. They only know that it exists because of its gravitational effects on the universe at large scales. In essence, dark energy behaves like a repulsive force. Unlike gravity, which pulls things together, dark energy pushes them apart. Its influence becomes more dominant over time as the fabric of space continues to stretch. The more space there is, the more dark energy there seems to be, and the faster the universe expands. There are several hypotheses that attempt to explain dark energy. One of the most enduring is the concept of the cosmological constant. Originally introduced by Albert Einstein, this idea suggests that empty space itself has an inherent energy, a constant that causes a steady, uniform repulsion. Though Einstein once called it his greatest blunder, modern cosmology has resurrected the idea as a possible explanation for the observed acceleration. Another possibility is the existence of a dynamic field known as quintessence. Unlike the cosmological constant, quintessence would change over time and space. Potentially varying in strength as the universe evolves, this field would fill all of space and influence the expansion rate, though it remains entirely theoretical at this point. Some scientists take a different approach, proposing that dark energy might not be a substance or field at all. Instead, perhaps our understanding of gravity itself is flawed on cosmic scales. In this view, the equations of general relativity may need to be modified, and what we perceive as dark energy could instead be a sign of new physics. Let's also quickly look at how much of the universe is actually dark energy. According to this chart, ordinary matter makes up 5% of the universe, dark matter makes up 27%, and dark energy makes up 68%. That means the matter that makes up the stars, planets, and people is only a tiny sliver of the cosmos. The majority of the universe is unseen and unexplained, dominated by forces and components that lie beyond the reach of current instruments and theories. Dark energy isn't just a curiosity. It plays a vital role in determining the future of the universe. If its repulsive force continues to dominate, the universe may end in a big freeze where galaxies drift so far apart that stars burn out and the cosmos become cold and dark. There's also the, now unlikely, possibility that the energy could reverse or disappear, causing the universe to slow down and collapse in a big crunch. While evidence currently supports continued acceleration, the ultimate nature of dark energy remains uncertain, and with it, our cosmic destiny. Once again, returning to astrophysicist Neil deGrasse Tyson, he points out that dark energy is a humbling reminder of how much we have yet to learn. It challenges the very core of our understanding of space, time, and the laws of physics. While we can describe its effects mathematically, we still don't know why it is or why it exists. In a universe where invisible forces guide our fate, dark energy stands as one of the most profound and elusive aspects of reality. As our tools grow more advanced and our minds more curious, perhaps we will one day uncover the secrets behind this silent engine of cosmic expansion. With that being said, out of all of our end-of-the-universe theories, two are more likely to happen, either the Big Freeze or the Big Rip. This is if we take in consideration that our universe is its own little bubble in a sense. We finally arrive at the Big Rip. The concept was born from observations in the late 1990s, as we said, when astronomers discovered the universe's expansion was not slowing down, but actually speeding up. This unexpected acceleration, which was attributed to dark energy, which is an unknown force that appears to counteract gravity on cosmological scales. While the exact nature of dark energy is still a mystery, it is currently, as we said earlier, 68% of the total energy content of the universe. In most models, dark energy behaves like a constant repulsive force, sometimes described by Einstein's cosmological constant, exerting a steady pressure that accelerates the expansion of space. However, some theoretical models propose that dark energy might become stronger over time. If this turns out to be true, the expansion of the universe could accelerate so violently that it would eventually rip apart all structures in the cosmos. To understand how the Big Rip could occur, scientists look at a key value called the equation of state parameter, represented by the symbol W. This parameter relates the pressure of dark energy to its density. If W equals -1, dark energy acts like a constant force, consistent with cosmological constant. But if W drops below -1, the model enters what's known as phantom energy territory. In this scenario, dark energy's strength increases over time. The more the universe expands, the more dark energy fills space, and the stronger it becomes. This feedback loop leads to runaway expansion, eventually overwhelming all the forces that hold matter together: gravity, electromagnetism, and even nuclear forces inside of atoms. Think of it like a balloon getting filled with air, more and more air until it rips and pops. If the Big Rip scenario were to unfold, it would follow a chilling progression of events, each stage marking the destruction of increasingly smaller structures. Billions of years before the end, galaxy clusters would be the first to disband as dark energy overcomes the gravitational bonds between them. Millions of years before the end, galaxies themselves would begin to fall apart. Stars would drift away from their galactic cores and no longer be held in orbit. Thousands of years before the end, solar systems like ours would unravel. Planets would break free from their stars and drift into the void. Minutes before the end, stars and planets would be torn apart by the expansion of space itself. Even the atomic bonds that hold matter together would begin to fail. A fraction of a second before the end, atoms would disintegrate, subatomic particles would scatter, and even space-time itself would rip apart. At that final moment, known as the Big Rip Singularity, the universe would cease to exist in any meaningful form. At present, the Big Rip remains a theoretical possibility, not a prediction. Observational data from missions like Planck and the Sloan Digital Sky Survey currently suggests that the equation of state for dark energy, W, is very close to -1. This would support a more gradual future expansion, possibly leading to a big freeze or heat death scenario, in which the universe expands forever but never tears itself apart. However, due to the limits of our knowledge and technology, we cannot yet rule out the possibility that dark energy might behave differently in the distant future. If future observations determine that W is significantly less than -1, the Big Rip becomes a much more realistic concern. The Big Rip, though terrifying in its implications, offers a fascinating glimpse into the unpredictable nature of the cosmos. It highlights just how much of the universe is driven by forces we do not yet fully understand. As astrophysicists continue to study dark energy, they inch closer to answering profound questions about our ultimate fate. Finally, to conclude, let us once again return to the words of astrophysicist Neil deGrasse Tyson. The universe is under no obligation to make sense to you. The Big Rip, if true, would be a perfect example of just how strange and humbling the universe can be. It is a reminder that our cosmic story, as grand as it seems, may still be hurtling towards an ending beyond comprehension.